Okay, welcome to this lecture on Maxwell-Boltzmann speed distribution. Uh, the distribution itself, it's a probability function where it shows how the velocities of molecules are distributed for a certain temperature. So, for example, you have these air molecules in your room, and they're kind of running around with very high velocities, right? 200 meters per second, 300 meters per second, 500, or even a kilometers per second. And that velocity actually depends on temperature. As you increase the temperature of the room, the kinetic energies of these molecules also increase because they start to run around with very high velocity because they absorb the heat energy that you're giving to them. So Maxwell-Boltzmann distribution, we can start with simply drawing how it looks like. So over here, I'm going to write the function which depends on the velocity. And on the x-axis, we have the velocity v. So for example, if the velocity is 0, of course your kinetic energy is 0 and you will not find anything right there. So this would be, for example, at a particular temperature T1. So this has a long tail. Actually, doesn't go to 0 just like that. There's a tail which extends like that. And then you increase the temperature. What happens is that this entire thing starts to shift to the right. So then this is T2, and you increase the temperature again, it shifts. And gradually, this one moves to the right. So the most probable velocity will start to move to the right. In this case, we have T3 is greater than T2 is greater than T1. Okay, so so what does this mean? It means that if I take a certain velocity interval, so when I say that certain velocity interval, it would mean, for example, let's say between 100 meters per second to 200 meters per second. And we can have an estimate of the fraction of molecules that are traveling with that velocity. Okay, so for example, if I say this is between 200 to 300, and if I take the amount, if I count the number of molecules within that, that would be a fraction of the total number of molecules. So maybe 10% of the molecules are traveling in the room in that velocity regime, right? So you can do let me just first write down what FV looks like. So FV would look like this is my FV, so which is 4 pi m over 2 pi kt raised to the power 3 over 2, then v square e to the power minus m v square over 2kt. Okay, now this is like a probability distribution, so we don't have any what you call it, you have to multiply it with some kind of velocity or velocity square to get an idea of what it truly represents. We'll get to that in a few minutes. So first, let's look at that. So this is your the probability distribution, and then what we can do a number of things with them. So let me just erase this graph. All right, let me just erase this graph, and I'll show you what we can do with them. So let's say that this is the high energy tail, right? So this is your velocity increases that way, and this is the probability distribution right here. So for example, if I simply have a velocity I determine, maybe 500 meters per second, maybe a kilometer per second. So all these things, they represent right there is, so this one represents number of molecules greater than that velocity, VA. As I said, the VA is like 500 meters per second or a kilometer per second. Anything that you that you do. Right here is my VMP. What does VMP stands for? VMP stands for most probable velocity. Most probable because you have, if you take a range right there, range of velocities, maybe 300 to 400 meters per second. So you would get most of the fraction of the molecules there. So maybe, maybe 20%. So there'd be more of them there compared to like 10% or 15% or 5% or 0.1%, right? So how I can find it? Well, you know that there is a curvature right there, and basically if I take the differentiation, if I differentiate this thing and makes it equal to 0 because the slope is 0 right there, then I can get the most probable velocity over there, right? So let me write this down here, maybe on this side. VMP, the most probable velocity, can be found by taking derivative. Let me use another pen. Taking derivative with respect to V and setting it to 0. And you have to solve it. Okay? So that's the most probable velocity, and we're going to do that. What I also want to find out is there are two things. One would be V average, and the other would be V RMS, actually root mean square velocity. So first I want to, actually I didn't want to erase this over here, but I might have to. So what I will do, because I want to keep this for the timing, so what would happen is that just so that you know, the average velocity would be actually a little bit higher than this one. This would be V average. Okay, V average. And the V average would be, I'll just erase this part here. V average would be, what you do is that you take the V and multiply it by the velocity distribution, and you go to 0 to infinity. That's our V average right there, okay? And then V square average would be simply you take this entire thing. Let me write it down in blue. V square FV dV, and then if you take VRMS, is basically that, it will be that VRMS. So and turns out that VRMS is even a little bit higher, which is VRMS would be over here. And we're going to actually calculate. I'm not going to do too much of physics explanation for this. I'm going to keep this within mathematics regime so that you know how to derive these three things: V most probable, V average, and V RMS. Okay, so let's start with something that is which is what you call it the easiest of all of them. The easiest of all of them is actually the most probable velocity. So what's the most probable velocity? We already said that it's we need to have you need to take the differentiation of this expression right there, right? So let me just do one thing very quickly. What I'm going to say is that I'm going to define this as A. Remember, there is a 3 over 2 here. Define this as A. So that solves a lot of my problem. So again, let's try most probable velocity. Now we're mixing the word velocity and speed in this case. So you know there is, as you know, that the velocity changes direction. It becomes kind of, you know, it's continuously changing direction. So we really should be talking about most probable speed rather than most probable velocity actually. But let me continue with this. Let's not worry about this for the time being. So I have this function and I differentiate it with respect to V. So what we have is that I'm differentiating this guy right here. So A, we have V square, and then you have e to the power minus m V square over 2kt, right? Okay, so keep this in mind. I'll just use that later on. Again, very quickly, what do I have? I have A, I can take A common. Let's not worry about this. I have 2V, I'm taking differentiation of this guy. Keep that untouched. Okay, and then keep this untouched, V square, and differentiate this guy. And what you have is that this will come, something will come in front, right? So what you got? You got mv squared coming in, but you differentiate mv squared, it will be 2mv over 2kt, right? And then the exponential stays as it is. And I equal to 0, A goes away, okay? A goes away, and what you have is your I can start looking at this equal to that, right? So let me just write this out. So I have 2v e to the power minus mv square over 2kt. Actually, I really don't need it. You can see that that one also gets cancelled. So I have simply, this is v cube. So I have 2v on this side and v cube m over kt on this side, right? Okay. So you can see right away that v square would be equal to 2kt over m. So v is simply root 2kt over m. So this is the most probable velocity. That's not the average velocity, but what it means that if I just catch, not catch really, determine the velocity of a molecule, the most probable, like maybe 10% of the time could be most probable for, because the other ones would be much lower than that. So it would be at that velocity, whatever that velocity. So you put the time in here, and this is the mass the molecular if it is an oxygen molecule O2, you find out what the mass is, and then the temperature could be like 300 Kelvin or whatever the room temperature, or wherever you are, that you put that temperature, and K is Boltzmann's constant. So that's the most probable. So as I said, that this is possibly the easiest one of all that we're going to do. So let's quickly go now to the average velocity. So what's the average velocity? Again, what I want is V average equals, I am going from 0 to infinity, V multiplied with the function. You need that dV because we are looking at individual segments, right? So what happens here is that you have, this is your probability distribution. So what are we doing? We said that, well, take that for example. So this is my dV. So this is dV is right there, by the way. That's your dV. Okay, and then this is the function value right there. Okay, so what are we doing here? Well, this what we're doing. So for example, dV, it could be, for example, 100 meters per second to 200 meters per second, right? If you take that and you say, how many, so what's the probability that between 100 and 200 meters per second, how many of the total, how many molecules you're going to get? Maybe it's 10%, okay? So that's like 0.1 right there, okay? From here to here is 0.1. So now what happens? This is V average. So I'm getting all these numbers that are going to get, which the molecules which have velocities between 100 and 200, they get weighted. They get weighted by that 0.1. So so basically what I'm saying is that how many of them are in that category between 100 and 200, and that would be like maybe 10%, right? But then I have something else right here that may be 15% between 200 and 300. That's 15%. So they're slightly higher. So what I have to do is that an average, 10% will have 100 to 200, 15% will have 200 to 300, and I have to weight them. When I'm going to do the averaging, I have to weight those velocities, so that there would be a little more of those guys, right? Little more of those guys. So it would be, let's say, 0.1 times that, all those others, plus 0.15 times all those others, and so on and so forth. And then I can take an average of all those. When I add them up, that would be my average in the end. So that's what we have here. So let me just quickly write, this is 0 to infinity, and then I have a V cube e to the power minus m v square over 2kt dv. Where that v cube comes from, remember there's a v square here, so v squared times v, that gives you v cube, right? So let me do a couple of things here. I need some substitution. Let's take v cube to be x, okay, and alpha equals m over 2kt. That solves a lot of writing this over and over again, so I can put that. So then v average becomes a 0 to infinity, and then you have v cube e to the power minus alpha x dv. Okay, alpha x dv. It looks very simple, right, over here. The problem is that you have to solve it. You have to do integration by parts. So how can I do this one, integration by parts? But before I want to do this, let me think about this a little bit. Remember, I have v cube equals x. So I need to change that to x or something like this. But if I do this, I need to change dv also. So let me do this way. V cube equals x. So 3v, sorry, not v cube equals x. I beg your pardon. I don't want to take v cube equals x. That doesn't solve the thing. Let me go back and change it to v square equals x, okay? V square equals x. My apologies. Yeah, because that won't work. I don't want that 3v square in there. So v square equals x. That's what I want. So if v square equals x, I get 2v dv equals to dx. I'm going to convert everything into dx in a second. So, and so the dv gets converted into dx over 2v. Okay, dx over 2v. All right, so let's go up here. Let's go up here and just write this down again. So my v average will be equal to a goes outside 0 to infinity, because you know the limits I think don't change when I do that. V, I have to, because v cubed, so I still have a v x e to the power minus alpha x. Okay, I have dx over 2v. Now the v cancels out, which is great. So I end up getting in the end a over 2, keep that there, 0 to infinity, x e to the power minus alpha x dx. I think it's okay, right? I think I'm all right. All right, now it looks something I can manage with integration by parts. So let me write this down here. Now employ integration by parts. So how's my integration by parts? Well, you know that it's I always have to go back to something like this. U dv equals uv minus, I have v du, right? U dv, that's what I want. U dv is uv minus v du. All right. So what is u and what is v? You have to kind of fix it. All right. So what I can do here is that I can say x is u and dv is e to the power minus alpha x. Okay. So if dv, so I need to find out what v is. So let's look at what v is. So this is my u and this is my dv. So the first u stays x by itself, but I need to figure out what dv is. So I need to take an integration of that. So this is v is, remember that because we have limits over there, you don't need a constant or anything like that. You can keep it as it is. So this is v, this alpha comes on the bottom, e to the power minus alpha x over alpha, right? So that's my v. So let's go ahead and finish this up. So remember that actually not this. I want this one, right? This one. So you have a over 2, which is great. Keep that a over 2. And then you have u which is x. So I keep x. And this is a negative, so let me get this negative out here. e to the power minus alpha x over alpha, and I go from 0 to infinity. Actually helps 0 to infinity. You can see right away that this would be this. We'll get back to it in a second what that is. So minus v du, I again go from 0 to infinity. Okay, so and then let me write this down first. So what's my v? My v is e to the power minus alpha x over alpha, and I want to have it with respect to dx, right? All right, so, and then this is a negative, so I get a plus over here. What about this first guy? Well, the first guy is if I put infinity over here, e to the power minus infinity is 0. And then for the second one, if I put 0 here, so that's 0 also. So if the first one would be infinity times 0 is 0, and the second one would be 0 times whatever it would be 0. So this entire thing goes to 0. I don't have to worry about it. That's a big relief. That's a big relief. This entire thing goes to 0 once you put the limits in there. What about this guy here? Well, that's the one that will give us our final answer. So let's go ahead and start writing down what that is. So we have, remember, oh sorry, there's an remember there is an a over 2 over here continuously. So what happened? We have a plus a over 2, which is good, all right? And then you have to do this one. It will be e to the power minus alpha x over alpha square, because one of these alpha will come down below, and you go from 0 to infinity. Go from 0 to infinity, right? Okay, so we just have to do this guy. I just have to make sure that I don't, I have a negative over here. I need that negative right there. Yeah, I need that negative. So because, this minus alpha, so minus alpha squared. So again, the first term is e to the power minus infinity, that's 0. But the second term, e to the power 0, will give you 1. And there's a negative in front. So first term minus the second term, so minus minus plus. So it would be simply a over 2 alpha square. A over 2 alpha square. Okay, let's start to put everything in and see if what's the final result. What's the final result? So remember what my a is. So I have to go back and check what my a was. Remember, a was this entire, I think we did entire 4 pi, then m 2 pi over kt raised to the power 3 over 2. So a was, so this is 4 pi m over 2 pi kt raised to the power 3 over 2, right? All right, that's my a. And then I also have to remind me what my alpha was, right? So my alpha was m over 2 kt. So my alpha was m over 2 kt whole square. And you have to simplify it, right? You have to simplify it, and it gets what do you call it? It gets a little bit complicated in some ways. That you have to have. Actually, the screen went black a little bit, so I don't know how I'm recording it. So 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 this is a technique, and what I found out is what helps me is to break everything in terms of um, what it represents. So what do I mean by that? See that 4 pi. So I write 4 pi over here. Okay, and then this is 2 pi 3 over 2. So what I want to do is that I want to write down here 2 pi, that's 1 2 pi, and there's another 2 pi which is 2 pi to the power half. Okay, 2 pi to the power half. All right, so then we have m over 3 over 2, but see there's an m square here. Okay, m square here, and I want to take that m square upstairs, so this would be m to the power minus 2 right there. Okay, then let's look at kt here. Kt is 3 over 2. This kt, if you take upstairs, will be kt square. If you bring it down, it would be kt minus 2. So I have that. All right. So so that's that. And then I have I have here I have a 4 which goes up, and then 4 which goes up, and this is 4 goes up, then 4 divided by 2. So I'll just leave it at that, 4 divided by 2, so that I have everything out here. See, so as I said, that I want to write out everything as break it up, and that would help me. Look at this now, what happens. So I have 2 pi cancels out, which is okay. Pi cancels out, so I possibly will have a pi. I will possibly have a pi in the end. So 4 times 4 is 16. 2 times 2 is 4. 16 over 4, that gives me 4 upstairs. Okay, I have a 2 pi to the power half. Keep that there. M 3 over 2 minus 2 gives you m minus half, actually. All right, and kt minus 2 plus 3 over 2 gives you also minus half. So this thing will go upstairs. Okay, they actually will flip. So what about 4? Well, 4 is 2 square. 4 is 2 square, so I can write 2 square times 2 minus half over pi half. Now look what happens. I have here kt half over m half, right? M half. Okay, so what do I get in the end? Let me see if I got if I can make them. So I have a 8. You have the kt is okay, and then so this would be 2 minus half would be two. So what do you get here? So 2 minus half is again 3 over 2. Okay, 3 over 2. So let me just say this: 2 times 2 to the power minus half is 2 to the power 3 over 2. So really speaking, this one would be, if you look at it, 2 to the power cube, which is 8. So that gives you root 8. Okay. So this answer in the end comes out to be 8 kt over pi m. Okay, so my final answer is V average is 8 over pi and then KT over M. So KT over M is what it determines the unit, and 8 over pi. Notice that 8 over pi is between 2 and 3. So we got the average velocity was root 2 KT over M. Now we have 8 over pi KT over M. The next video we were going to determine the VRMS, and then you'll see that will give you root 3 over KT over M, and that's a little bit more difficult one to derive, but we're going to do this. We need that, and so I will end this video right now because we already have done quite a bit. So, and let's just now prepare ourselves to go to find the VRMS. Okay, thank you.